Hey guys, hope everyone had a great spring break. And we're gonna get right on into this. I know some crazy stuff going on with all the COVID-19 stuff, but we're just gonna and jump into some science here. So what you need for today is you're gonna need a writing utensil, and you're gonna need your ecto and endothermic reaction notes page that you were given on the Friday before spring break. So if you don't have those, go ahead and pause this video and get those out. Otherwise, we'll go ahead and get started. So we're going to be looking here at energy, and one of the things that we know is that sometimes when you react to substances is that it doesn't just produce new products. You know, if you take, let's say, wood and oxygen and you burn them, you do get carbon dioxide and water. For instance, the wood, the carbon dioxide, and the water, but you also, and so some reactions tend to give off a lot of heat, and those are what we're going to call exothermic reactions, and some reactions tend to absorb a lot of heat and get cooler, and those are called endothermic reactions. So starting off, our first idea here is that we're going to say a chemical reaction is called an exothermic reaction if it gives off heat. And we're going to say a chemical reaction is called an endothermic reaction if it absorbs heat. That is, it gets colder. So exothermic reaction, classic cases, we're talking about like fire. So, you know, when fire happens and it gives off this huge amount of heat as we go through it. Endothermic reaction would be more like one of those cold packs that you put on your leg. There's a chemical reaction that goes on inside of that, and whenever that chemical reaction happens, it gets colder. It absorbs heat in and gets cooler. So in the sense of doing this with like a chemical reaction, let's talk about like burning alcohol. So here we have the C2H5O8, and we're going to react that with oxygen gas, which is O2. When you do things, you get CO2 and H2O. We've balanced the equation. But let's say we start off with cold alcohol and cold oxygen. Whenever we burn those, we don't end up with cold things afterwards. We end up with hot things afterwards. We end up with hot water vapor, you end up with hot CO2. It's because the products, what you end up with, are warmer than the reactants, what you started with. This is giving off heat, and so we consider this to be an exothermic reaction. Now, if we did this reversed, if we took potassium nitrate, even some warm potassium nitrate, and we put that in water, it would decompose, it would break down into K plus ions and NO3 minus ions. So it breaks up into these two parts in this chemical reaction. But when it gets colder, so we start with a warm potassium nitrate and end up with cold dissolved potassium and nitrate ions. And so since these products are colder than the reactants, we consider this to be an endothermic reaction. Now, to understand why these happen the way they do, we're going to look at this idea of what types of energy are in the chemical bonds that are in the intramolecular forces of the substance. So chemical bonds have a type of potential energy called chemical energy, or we could rephrase that by saying that chemical energy is the type of potential energy that's stored in chemical bonds. Now, if we have an exothermic reaction, that is a reaction where the energy goes up, when the thermal energy goes up, that means the chemical energy must be going down. So we're going to say it this way. If the chemical energy in the reaction of the bonds decreases, then that means the thermal energy increases. So it's exothermic. But if the chemical energy of the bonds increases, then it means the thermal energy must decrease. So exothermic reactions happen when it gives off heat because the chemical energy goes down. Endothermic reactions happen because the thermal energy goes down, which means the chemical energy has to go up. Now, to really see this, let's go a little more in depth to explain why. So first, let's just look at chemical energy. We know this. Chemical bonds are attractive forces between atoms. They're ones that pull them together, that hold them together here. They are those intramolecular forces like ionic and covalent bonds that hold atoms together. But here's the way they work. So this graph right here has the distance two atoms are apart on the x-axis and has the amount of chemical energy on the y-axis. So in step one right over here, we have two atoms that are very far apart. They're not bonded together. And so the intramolecular forces between them are going to pull them together. So this atom wants to attract to this atom right here, and we can see that they're attracting. And then eventually they attract so close that they bonded together. But let's think about what we said. We know that that what's going to happen then is that as they bond, you can see the chemical energy goes down. The chemical energy decreases as the bond forms. Now, the reason why is, remember that it's a potential energy. Potential energies are always increased when you go against the force. So since these attract towards each other, it means that when we start off far apart and we pull them towards each other, they're moving with the force. And if they move with the force, their potential energy drops. And so you can see their chemical energy is dropping as they move toward each other. But what's happening up here? There's something that's going on in this part. Well, what's happening is if we push them too close together, they don't pull against each other. They're actually going to push against each other. What specifically happens is that the positive protons in the middle start pushing out on the other positive protons if we get too close. And then if we move them closer, we're actually going against the force, and so the potential energy goes up. There's this nice little sweet spot right down here, and that sweet spot is where the bond is going to form, because that's the spot where they're at their lowest potential energy, and so they're at their most stable state. So we can see that if we make a chemical bond, we have two atoms that are far apart and we bond them together, their chemical energy is going to drop. It's going to get lower. So chemical bonds, we know, are attractive forces between atoms. When chemical bonds form, atoms move with that attractive force. Therefore, when new chemical bonds form, the chemical energy is going to go down. Okay, what if we break bonds? Well, because we said chemical reactions happen whenever you're making or breaking chemical bonds. So if we were to break bonds, they're starting off down here, and we're going to separate them apart and move them up here. We're going to get them from bonded to unbonded. Well, since they're attracting, when we separate them, we're moving against the force. If you move against the force, you increase the potential energy. And so we've increased the chemical energy, and we can see that here. As we separate them apart, the chemical energy goes up. Okay? So summarizing that, chemical bonds are attractive forces in atoms. So when chemical bonds break, atoms move against the attractive force. Therefore, when old chemical bonds are broken, chemical energy is going to increase. It's going to go up as we go through there. So how does this tell us about endothermic and exothermic reactions, whether it gives off heat or takes in heat? Well, basic idea is this. If we have two substances like this H2 and O2, they're going to have a certain chemical energy to start with. And at the end, when they form new things, the chances of that chemical energy being exactly the same thing is pretty much zero. It's probably going to be a different amount. In this case, the chemical energy ends up being a little bit lower than what it was before. So when any chemical reaction happens, the new bonds that are formed have a different chemical energy. Sometimes that chemical energy goes down, sometimes that chemical energy goes up. So we also know that energy can't be created or destroyed. The total amount of energy has to stay the same. And so that's what we're showing with this red line. We're showing the total energy stays the same. But that original chemical energy has to be some type. Well, what is it? Well, it's thermal energy. And so what's going to basically happen here is that this amount of energy is going to be the thermal energy it starts with, and this amount of energy is going to be the thermal energy it ends with. To show you another picture of that, we'd look a little bit like this. The chemical energy here is going to start relatively high. The thermal energy is going to start relatively low. When the chemical energy goes down, because the total stays the same, the thermal energy has to get bigger. So if the thermal energy gets bigger, then we have had an exothermic reaction. It's getting warmer because we decreased the chemical energy, which means we had to increase the thermal energy. So exothermic reaction. So in general, that's how we're sort of going to say it here. Exothermic reaction happens when the chemical energy starts high and then ends low, which means the thermal energy has to start low and has to end high. And so thermal energy increases, it gives off heat. It's called exothermic. So in this particular reaction where we're burning the alcohol, that's why it's exothermic. If it gives off heat, then we know the chemical energy went down. And if the chemical energy goes down, thermal energy goes up. What about endothermic? Well, it's literally just the opposite. In an endothermic reaction, the chemical energy starts low, but then gets higher, so that the reactants have a very low chemical energy and the products have a much higher chemical energy. And if the total energy stays the same, then that means the thermal energy has to drop because the total can't change. If I started off with 1 unit of chemical energy and 7 units of thermal, I ended up with 6 units of chemical. Well, how much thermal do I have to have? Well, it has to be 2 because I started with 8 joules of energy and I have to end with 8 joules of energy if it's a closed system. We're going to treat these all as closed systems. And so that's what happens in endothermic. But that sort of raises a question. So let's suppose that we have something like this burning reaction where we start off with a large chemical energy and end up with a small chemical energy. Well, we know that systems that are uncontrolled always want to move to a more stable state. And there are two ways to do that. We'd have a lower potential energy, or the energy can become more evenly spread out. In this case, we're getting a lower potential energy because that potential energy, that chemical energy, drops. Well, if that's true, then why don't things just randomly just catch on fire on their own? Paper and oxygen, if you burn them, is exothermic. And if they're exothermic, that means the chemical energy is dropping, which means it's more stable after it's burned. But if I just have paper out in the air, it doesn't just randomly light on fire. Something has to happen to it to make it do that. We have to add a spark or some sort of energy source, rub two sticks together or something like that to be able to get it to ignite. Well, the reason why is we have to remember that in a chemical reaction, we have to break old bonds and then make new bonds. But if we're doing that, that means we have to break them first. There's sort of an in-between state where basically the bonds have been broken, but new bonds have not yet been formed. And so we're going to call that the activated complex because it's like it's active. The chemical reaction is going on. It's not done yet. It's partially halfway done, but it's now. If we think about what's going to happen with an activated complex, they have to move to break the bonds against the force, which means the chemical energy has to go up. And so we can see here the chemical energy is going to go up to the activated complex. And then when it forms new bonds, we're going with the force, so the chemical. And this is going to be true in every single chemical reaction. It's always the case that the chemical energy first goes up as you break the bonds and then comes back down as you make new bonds. And so that activated complex always has the highest chemical energy. And this helps to explain why reactions don't just sort of typically happen on their own, is that to react, they first have to become a little bit less stable. We have to add a little bit of energy to get it going. Now, admittedly, sometimes there's just enough energy just in their environment for this to happen. If you take a sheet of paper and you heat it up to, say, 500 degrees Fahrenheit, it will just ignite on its own. And the reason why is because there's enough thermal energy to sort of get it up over this activated energy hump, to give it enough energy to get here. And then once it gets up to this activated complex, it's going to get more stable by going down to the products right here. This is sort of why you have to start a fire.